Welcome to this video on linear equation systems. In this video we will discuss how to work with matrices in linear algebra in Python using scipy.linalg, and especially we will discuss how to solve systems of linear equations. So as normally I will import NumPy and some plotting tools, and then I will import the timing module to do some timings, and then I will input this linalg sub-package will be central for what we will be doing today. I will also be importing a local package which sort of will show some details about what can happen. But let us think about economic models. So a lot of economic models can be thought of in terms of systems of equations. And the question here is how to solve these. A very simple example is a market equilibrium where we have a supply curve and a demand curve. You say that the supply curve, that is Q, that's the supplied quantity, is equal to 5 plus a third of the price. And on the other hand, there's a demand curve, which is again is the demanded quantity, 10 minus 2 times the price. So an upward sloping supply curve and a down sloping demand curve. We can think about these two equations as an equation system. They must be fulfilled at once, so we can write them up as two equations, or we can write them up in matrix form. So there's an equation in X, and there's a matrix A, and there is a right-hand side that's B. And solving for the equilibrium simply means solving for this X, and we can do that simply by looking at our equation, taking the inverse of the A matrix and multiply it with B. So if we want to do that, then we have to set up the A matrix. That's simply a NumPy array, that's 2 times 2. The B right hand side, that's just a NumPy vector. And then we can do the inverse of A, and we can do the matrix multiplication with B, and then we can print out our solution. So that's the simplest approach we can take. You can pause here, and then you can try to do it in the case where we have a larger demand, where the demand curve is instead 20 minus 2 times P. I will not do that here, but you can do it on your own. More generally, what we are thinking about here is that we are solving matrix equations with n equations and n unknowns. So this big system here, where A is some square matrix, and B is our parameter vector, and X is the vector of unknowns. Specifically, we can look at this 3 times 3 example down here, which might be something that we for some reason want to solve. Here I've just set up the two matrices as we have them, and then we can of course do exactly as we did before, compute the inverse and find the solution this way. There are sort of reasons why this is often not a good idea to do. This inverse here can sometimes be numerically problematic. So actually it's better to use a direct solve method, which is in this scipy.linalg. We simply say that you want to solve the linear equation system A times B equal B, and you want to give it the A matrix and the B vector. And then you print out the solution, and we check that we get the right solution. So these two things give the same results here, but sometimes this solve method here might be better. Just to take an example of this, here I have a somewhat weird H matrix. I have a known answer that I'm putting in, and then I'm calculating what my right hand side should be for this C to be the answer. And then I try to inverse it and get back to the answer again. So I do it either by taking the inverse of H here and multiplying with my right hand side, and then I subtract what I know to be the solution, or I do it with linalg solve. And if we do this, then actually you can see that we get rather large errors in using the inversion, while the errors are much smaller when we use solve. You don't need to understand why exactly that's happening, but it's because there are some operations that are numerically imprecise when you do the inversion. So always use the solve instead, unless it's sort of a small choice stuff that you are doing. The third option is you can also perform what's called an LU decomposition. I will talk a bit more about that beyond, and then you can solve the equation system with that. This requires 2 lines of code. First, you do an LU factorization or decomposition of the A matrix into this LU decomposition, and then a sort of pivoting list that SciPy is using. And then afterwards, you can call the LU solve using these 2 previous outputs and inputs, and then the right hand side. If we run this, we again get the right solution. This is sometimes smart because it's it only requires doing the decomposition once, while you can now solve for many B's once you have done that decomposition. So in that sense, it's good if you have different right hand sides but the same left hand side matrix. Then you can do this fast. And actually, in the current implementation that I have of SciPy, I think actually that the LU factorization and solving is just faster than the direct solving. I don't know exactly why. That must be some kind of checks or some time with other stuff that's doing in solve. But we can sort of here I'm running a time it of these things, and we can see that doing the LU solve is about 4 times faster than doing the solve itself, and it's also not that expensive to calculate the LU decomposition. So overall, it's actually very good to use the LU here. The solve is faster in sort of terms of writing the code, and on your computer and in your implementation, it might also be faster than doing the LU stuff here. I don't know why that is actually why these 2 are actually even combined faster than just a direct solve. That shouldn't be the case. I don't know exactly what's going on here. Okay, so now a task for you. Have a look at this code below. Now I'm creating multiple right hand sizes, and then we want to sort of solve each of them and be sure that we have the right solution each time. And I want you to do that first with linealg.solve and afterwards with linealg.lusolve. So pause the video here and do that. Okay, I hope you have tried to do it. Let us see how we could do it. So if we want to do it with linealg solve, then here we're just creating an x that's equal to 0. So if I run this now, it's not successful. Solution is not correct. Okay, so I could replace this with linealg.solve, and then I could put in my A, and now I need to put in my C matrix here. And you can see now this could be successful. Then I could use the LU solve. So let's remember, what did we do there? There we first use this LU factor here, and then we use the LU solve, and this put out the LU and the PV, and we put in it like this here. So this didn't work. So what did I do wrong here? I put in the A instead of the LU. So now this is also successful. And now sort of what's inefficient here is that I'm computing this decomposition of the A matrix each time, but I could actually move it out before the loop, because the A matrix doesn't change in the loop. So I need only to do this once, and I still get the correct result. If you time it here, then you will see that this is of course faster than repeating this operation many times. Okay. So this is actually how you can solve linear equation systems in Python. You can do it the brute force way with doing the inversion. That's not the best approach. You can use solve. That's the coding-wise most easy approach. And then you can do the LU decomposition and solving, and that's a bit more involved, but the fastest the fastest thing you can do. And you can do this for these small equation systems we have looked at here, but also much bigger equation systems. In general, there's a lot of other matrix operations you can do. You can take the transpose, you can take a diagonal, you can do something where you fill out the diagonal of a matrix. Here I fill it out with zeros. You can create an identity matrix. This is a 3x3 identity matrix. You can take the lower triangular matrix of a matrix. You can take the upper triangular matrix of a matrix. You can find the eigenvalues, and there's many more operations you can do. So look up in the documentation if you need something. Okay, so this is actually the main part of this video. Then there are some sort of extra stuff for those that are interested. First of all, you might be wondering, how is the code for something like linealg solve and linealg in, how could they actually be written? And this is not exactly how they're probably done in SciPy, but this is an example of how you can write code that could do these operations here. So remember from your math teaching, you can create a stacked column stacked matrix if you take the A and then you stack the B column on at the end. So sort of you create this big matrix here. And now one way you can think about solving this equation system is by doing manipulation on this equation until it's on row reduced echelon form. And by row operations, you can sort of multiply each row with a constant, you can swap rows, or you can add one row to another. And then you want the A part of the matrix to be an identity, and then we will have the solution in the final column. So let's see how we could do that manually. So here I'm just taking my A matrix and stacking the B matrix at the end. And then I found out that if I do these operations in turn, then I will end up with an echelon form. So here I'm taking the first row and adding the second row 2 times, then I'm dividing the first row by 5, then I'm subtracting the first row from the second row, then I'm multiplying the second row with -1, and I'm subtracting the second row 5 times from the third row. And then if you do that, then you end up with this identity matrix in the A part, and you have our solution in the last column. So this is sort of how you could do it by hand. And actually, sort of there is something called Gauss-Jordan elimination, which sort of does this automatically. So in this local linealg package, I have implemented that, and sort of this spits out the right solution. And if you sort of quickly look into local linealg, the Gauss-Jordan, you can see that it's not that many lines of code actually that's required to do that. If you're interested in it, you can sort of look up what's actually going on inside here, and sort of it's just an optimized way of doing what I've done manually before. Sort of there's a specific order you do operations in, and then that works. So this is just if you wanted, if you needed to implement this from scratch. This is sort of the first thing you could do. They're probably doing something much smarter in SciPy underneath, but this is how it could look. The same approach works if you want to have the inverse. You just stack an identity matrix instead. So you take our A matrix and you stack in columns terms an identity matrix to the right. And then you can use the same Gauss-Jordan elimination, and now the last 3 columns here, that will be the inverse matrix here. So I can assert at the end that the last 3 columns of my C matrix here, if I multiply those with A, then I get an identity matrix. So that is exactly that this is a inverse of the inverse of A. Okay, so this is how you could code up something like what solve and inf is doing. You can also thought about what was this about the LU decomposition. What was that? What was I actually doing there? So the idea in this is that if A is a regular invertible matrix, then you can show that you can decompose it into a lower unit triangular matrix and an upper triangular matrix. So if you have the matrix A, then you can write it as L times U, where L has 1 at diagonals and 0 on top of the diagonal, and then some numbers below. While U has nothing lower on the below the diagonal, but numbers at and above the diagonal. And sort of if you want to do this decomposition, then there is a fixed way that you can do this. You sort of see that if you start with the first row up here, then because all these are zeros, then you know that if you multiply these together, then the first things that comes out here, then the U11 that must be equal to the A11. And then you can sort of deduce yourself through this algorithm that I'm written down here what all the numbers should be. Again, if you want to understand it in detail, have a look at the math here, and then you can sort of see how that can be done. Okay, so why do we want to split it up into these two matrices? That's because if we have that, then we can find a simple way to solve it. So this is the step you need to take to do this decomposition here. So when you have the decomposition, when we have performed the LU decomposition, then it's much easier to solve the equation system, because you can solve it in sort of steps, where you say first you think about an equation system where it's L times a vector y equal to b, and then you can solve by using forward substitution. You can sort of solve the equation system from top to bottom. So if you have something that's L times y equal b, then because you have this simple structure up here, then you can see, okay, the one that then you directly know the first solution, and then we can go on to say, okay, next we actually have the solution for this, and now this is coming on top, so we can get the solution for that, and then we can continue in this way, recursively finding the solution very efficiently. And of course, now we have solved a weird equation system, L times y equal b. We want to solve the full equation system, but now the idea is that what I wrote up here is I can write the a times x. I can write that as L times parentheses u times x equal b. So now I can actually say that if I have solved this, then my y was actually u times x. So now I need to solve for x in u times x equal y. And now you can do sort of the opposite. You can do this by backward substitution, which is a recursive system from the bottom to the top instead. So now you can see that, okay, if you start from the last one here, then you know that the solution must be what's on the right hand side divided by this. And then you can go one step back, and now this is a bit bad in the way it's written here, but then you will only have two elements here, and then you can do a similar thing. And then you can solve the equation system very simply. And again, I've implemented this in the local linalg package, and you can sort of see you do these three steps. You do the LU decomposition. You take the A, L and U comes out that have the right format, and then you can solve it by get the y by forward substitution. We're not caring about the y in itself, and then we can do the backward substitution, and we get the x out, and it's the same solution as we had before. So again, if you want to dig into this, you can look at the function. The LU decomposition implements the algorithm described, and the same thing goes on for the forward substitution. You see this is very few lines of code here, and you can sort of understand how this can actually be done in practice if you are a connoisseur in solving linear equation systems. If you just want to do it and not understand it in detail, that's also fine. Okay, sometimes you might actually not need to solve the matrix system precisely. It might be okay to solve it approximately. And there we can use an iterative solver, like Gauss-Seidel. So let me give you an example of how that can look. So we can always decompose a matrix A into a lower and an upper triangular matrix. So now these are additive and not multiplicative as they were before. So we just split it up in a lower and an upper, where we in the upper put zeros on the diagonal. And now you can write the equation system ax equal b as a left hand side, which is lx, and then a right hand side, which is b minus ux. So now the idea is that instead of sort of solving this equation system, we want to do this as an update step. We put in an x on the right hand side and we calculate what must the x on the left hand side be. And then we can put the left hand side x into the right hand side, and then we can continue doing that until we get convergence. So the Gauss-Seidel algorithm is that you choose some tolerance, then you set the iteration counter to 1, and you guess on x, guess something on that. Then you, from A, you get the L and the U matrix, and you set our Q and X to the guess. And then you calculate what must the right hand side be. That's the B minus U times our Q and X. And then you solve for yn. Then given this yn, you solve for yx in the equation Lxn equal yn. And if now our x is very similar to the one we put in, then we say we have found a solution. Otherwise, we stop. And again, we can sort of solve this equation system very simple, because this is this L matrix here. That's the lower diagonal matrix. So we can use forward substitution again. See above how we did that. And I've implemented that here, and we get the same solution as we had before. If we turn print equal true on, then we can sort of see that I'm guessing on 1, 1, 1, and then it spits out, okay, if we want 1, 1, 1, then the left-hand side x must be 0 minus 4, 19. But that's not the same as 1, 1, 1. So then we do it again, and again, and again, and again, and again, and eventually we converge to the actual solution. So this can sometimes be useful if the equation system is very, very big and therefore very hard to solve, but you only need an approximate solution to it. Then the Gauss-Seidel or something like Gauss-Seidel can be interesting. Okay, the final thing I want to mention is sparse matrices. So the case is that in economic models, if they get big, then the equation systems which sort of represent the model can also be very big. And sometimes there are many zeros in many of the equations. So there is many parts of the A matrix in the case we've looked at that would have had zeros in it. And in that case, it's irritating to work with this big matrix if it can be so big that you cannot put it into the memory of the computer, and therefore you can use sparse matrices. If approximately 70% of your matrix is zeros, then this can be a good idea. And the idea is that then you only sort of save information about where there are not zeros and what the values are, instead of storing the whole matrix. In scipy.sparse.linalg, you can sort of do the similar operations as we have done, just with sparse matrices. So let's give an example of that. So if you import sparse from scipy, then you can also import scipy.sparse.linalg, and then I here create some 1,000 times 1,000 matrix where I put some values on the diagonal, and I put some random values in some specific row, and I put the same values in some other row. This is just some random matrix. Here I created it as some specific form of matrix, a row-based list of lists sparse matrix. This is one kind of sparse matrix, and here I converted to other kinds of matrices. This is a compressed sparse row format, and this is a compressed sparse column format. So there's many different formats, and it's sometimes some functions want to have it in a specific format. So here I have it in 3 different formats, because that's useful for what we do a few cells below. But here I just put up the matrix. One nice thing you can do is sort of, these are very big matrices, so they are hard to see, right? But you can sort of plot how the matrix looks like. So here's a plot of the matrix where there is no coloring when there is zeros, and then you can see that there is color on the diagonal, and there is color on these rows here where we have put in some numbers. This is a way you can sort of represent a sparse matrix graphically. Okay, so now you might want to solve this, use this equation system and solve it in various different ways. So here I'm just creating a random right hand side, and then I want to solve it like it was not sparse. I want to solve it using the sparsity. I want to solving using sparsity plus explicit factorization, and I want to solve it with an iterative solver similar to Gauss Seidel. So if I want to solve it normally, then I solve a number version of the matrix. I did that up here, by the way. I converted the matrix to a number array, so I can just solve it normally. And here I'm timing how long does it take to actually, how many seconds does it take to solve this. Then I do it with sp-solve in linear, where I use one format of the matrix. Then I do it with a factorization in another format of the matrix, and then I solve it, and I time it each time. And finally I use this big G step, which is sort of an iterative solver. So let's try to run this, and you can sort of see that the numpy solve, so the non-sparse solve, is like 50 times slower than the sparse solve. So we're really saving a lot of time by using the sparsity structure. And you also see that even though the results are actually the same when you do the iterative solver, it's also very slow, as slow as actually doing the full matrix solution. So the two takeaways here are that using the sparsity can be very important. Iterative solvers can be very slow. Thank you. That was all for this video.